2 weeks.
And she's getting a new cast today.
Yeah.
So
Okay, well, thanks for having me. I don't think I have to introduce myself anymore. Chris does such a good job. I feel like I'm a really accomplished person when he starts me off like that. I will say that I personally have probably miles of electric fencing on my farm. I'm a big believer in electric fencing personally. And I know that figuring out when there's a problem is really a pain, and I'm really excited that we're going to do some work today on sort of diagnosing issues and understanding this kind of fencing. And I got the really fun part of this talk today where I get all of the definitions, which I know everyone is super excited for. So I've started you off with a really fun title, Getting into the Weeds. That's a little pun for you guys. If you don't enjoy it, that's okay, because it's the highlight of my day right there. I guess if you had a broken foot, the highlight of your day would be that low too. So how electric fencing works. I've drawn here an electric fence. I'm suggesting that red is hot and green is ground. It looks very similar to how I would draw any sort of electrical wiring in a house, right? The one thing I want you to know about electric fencing is that the way electric fencing works is essentially we're putting charge onto our wires. Not in our wires, but actually physically onto the outside of our wires. And what we're doing is we're basically creating this sort of a, let's see if I can do this, charger or energizer. We're using something as sort of a capacity. It has some amount of charge in it, and it's going to dump it out in pulses onto our wires. And what happens, ideally, when an animal touches it, is that they hit this hot wire, and the foot of the animal is also touching the ground, and that creates a circuit where the electricity jumps from the line to the animal, through the soil, and back to those ground wires. And so when people talk about completing a circuit, what they are essentially saying that's happening here is that those little charged particles are traveling through the animal because there's a lot of water in the animal. It's a really good conductor, and it's creating that shock that the animal feels. It looks a little weird on here, but whatever. It's pulsing the way it should be. The pulsing is really important on electric fencing. You know, if you look at your alternating current in a house, and this, it's sort of the same concept. We have charges going out, but not continuous, versus a battery, a DC circuit is a continuous charge. And there's a couple reasons that we look for this alternating or this pulsing scenario, and it's for safety reasons, primarily. This pulse basically allows something that's being shocked to release. It means that something that gets caught on this fence isn't stuck in the fence continuously. There's a couple reasons that electric fencing is really safe, and one of them is because it pulses. So we're not contained to that fence for forever. It's the same reason that we don't recommend barbed wire being electrified. Because once you get caught in barbed wire, you do not get out quickly. And if you get caught in that, you can't release just because the pulse ends, right? The other thing that happens with this fence that's really interesting, and we'll go into a bunch of these definitions in a minute here, is that this fence is high voltage, low amperage. And that high voltage, low amperage is much safer for us if we get hit than a low voltage, high amperage scenario. It's the reason we don't use the same AC current that goes through our house, right? We could have 120 volts and a bunch more amps, and we could shock the heck out of everything, but that wouldn't be safe in the same way that this type of fencing is. It is certainly still a deterrent. It's very unpleasant when you hit a hot fence. Anyone who's done it in here will attest to that. It's not my favorite thing to do. I tell people all the time that my husband is so afraid of all of this that anytime something has to be checked, it's always my job to touch it first. You know, I don't really know why. I wish I could explain it. Apparently I just am a weak person and I say yes. That's all we know. But legitimately, it doesn't matter how tough you are or anything else. Psychologically, it is extremely tough to touch an electric fence because we know how discomforting it is. I'm going to start out with some terminology. All of these definitions, do they have the Missouri grazing? Yes. In the Missouri grazing booklet that's in here, At the end, there's a bunch of terminology, and I pretty much copied their terminology. I tried to repeat it with a couple modifications so it makes sense to me. So if you ever are looking for some of this terminology, I think they do a really nice job with these definitions in there. And we're going to start out with the definition of energy just because, where else do we start but with the energy it takes to run this fence. Energy is by nature the capacity or ability to complete a certain amount of work. There's all different types of energy. Electrical energy in particular is what we're talking about on these fences. And what we're essentially doing with electrical energy is we're moving electrons to produce a flow of current around a circuit. And it takes energy to move those electrons out along that line. The amount of resistance on there we're going to talk about in a little bit, but basically there's always going to be something resisting those electrons moving out on that line, and that's essentially the work that's being done, is pushing them out. If it helps you to think about it, it's similar to having friction on something and then trying to push something across it. That's what that resistance looks like in an electrical circuit. And joules are something you'll see a lot of times on an Energizer box. It'll tell you so many joules of capacity or an output joules, and they're really just a unit of electrical energy. The work done is stored in the flow of electrons as energy. So basically, that flow of electrons is what's basically being the joules, or the energy in this situation. And 1 joule is, by definition, the amount of energy required to do approximately 0.74 foot-pounds of work. And foot-pounds is a really lovely term that someone used, trying to think how to describe it. Foot-pounds would be a terminology used when we used to do things by hand and we didn't have mechanization. That was how we basically forced work out. The quantity of joules released by an Energizer during each pulse determines how much effective power that Energizer has. So sometimes there's 2 things that you can see when you look at an electric fence. A lot of times it'll tell you a capacity, how much energy is stored in the Energizer, and it will also tell you an output joule. And both numbers are useful for different reasons. The reserve is how much it's going to dump out if we have a lot of shorts on the line, so that's important, especially if we're using a battery system and we don't have AC power continuously refeeding it. And the output joules is really how much can be sent out under ideal situations. So how much charge can we really push out on those lines? Watts. So joules, watts. Watts is basically the rate at which work is being done in an electric fence. 1 joule is the energy required to produce 1 watt for 1 second. If you want to think about watts, watts is essentially joules over time. So that's how we would say how much can sort of over a long period of time be produced in terms of energy. Not instantaneously, but over a longer period of time. And watts times seconds obviously equals joules then. Any questions on that? I think watts and joules are sometimes confusing because you purchase kilowatt hours when you buy power on your electric bill, but kilowatt hours looks an awful lot to me like joules, doesn't it? Because watts times seconds, seconds are hours, it doesn't really matter. So it just helps to kind of keep that in the back of your mind that they're actually very similar. What you're really buying is actually energy, not a rate of energy necessarily on an electric bill. But sometimes people think that's confusing because we don't use the term joule on our electric bills. Amps. Amps is the unit of electrical flow rate. The other way I would describe that is current. The speed at which those electrons are moving, how it's flowing through that piece of wire, and through is probably inaccurate, along that piece of wire. An amp flow rate of 6.28 times 10 to the 18 electrons per second is 1 amp. That doesn't help you at all. Those numbers are just really big. It just means that electrons are really small and we push a lot of electrons to get an amp of power. Coulombs. These are units of quantity in electricity. So a lot of times people will tell you a capacity in joules, but if you really wanted to think of it like all the electrons are built up inside a battery or something, what you're really actually looking at is coulombs. or all those electrons are built up together in one space. And again, this is that 6.28 times 10 to the 18th power of electrons, or 1 amp for 1 second. So basically, it's a lot of little electrons equals 1 Coulomb, if that makes sense. I think all of these are really sort of obscure terms for most people. It's hard to visualize a lot of this, but as we come here a little bit further down, I just want you to have all these terms in mind, because when we get to leaks and charges and stuff, it helps to sort of think about all of these terms to get a bigger picture on how electricity moves through these wires, or along these wires more accurately. Volts is basically electrical pressure. So I'm going to use the term pressure here because it makes sense to me. It's really how much that electricity is basically pushing out on that line. If we were talking about magnets, it would almost be like a charge. It's almost like thinking about how much area around it is being influenced. 1 volt is the force necessary to cause the current of 1 amp to flow through a resistance of 1 ohm. And we'll go over resistance next. But essentially, we have to push that power out at some rate, right? We're moving those electrons out. And that voltage is really how much work we're doing to get it across some amount of resistance. It's almost like the output from it, or the byproduct of it, I guess, is maybe a better way to describe it. Resistors are anything, electrical components, which due to material shape offers resistance or resistance to the flow of those electrons. This is probably the biggest one. I think we're going to look at this in the field today, a bunch of things, looking at how much resistance we have on a wire or a line. Anything that slows the flow, rust on a wire, or a wire that's frayed, a wire that is narrower than we want it to be, all of those things are going to add resistance onto that line, or an incorrect material even. Different wires and different metals have different resistances naturally associated with them, even though they're considered conductors. Basically, everything is going to, in some way, slow down the flow of that electricity. Ohms. Ohms are the unit by which we measure resistance. 1 ohm is the amount of resistance that limits the flow rate of 1 amp when 1 volt is applied to it. All of these are fairly arbitrary, but what we need to know is that if we have high ohms on something, we have high resistance. If we have high resistance, it naturally does not make electricity flow well. And if electricity doesn't flow well, then we don't get the voltage we need to shock an animal. Insulators. I'm sure we're going to look at a few insulators today. Insulators, by nature, is any substance that doesn't allow the flow of electrons, and it's used to stop electricity from leaking. And we'll talk about the definition of a leak in just a second here. But insulators are essentially something with really, really, really high resistance. And when we talk about electricity flowing, it's always similar to water. We're going to use a water analogy a little later here, but it's always going to choose the path of least resistance. So anytime we use a material that really, really resists the flow, it is by nature not the pathway that electrons are going to want to move through. A conductor, on the other hand, is a substance that freely allows the flow of those electrons. The less resistance a conductor offers, the better the conductor. So this is the opposite of an insulator. All of our wires that we're aiming to use are supposed to be good conductors. There's a lot of things that sort of fall in between a good conductor and an insulator. There's a lot of materials that do not necessarily get qualified as either an insulator or a conductor, or people will call them one or the other, but this is not a black and white issue. It's almost like there's a range here, and everything falls somewhere on it. But if we get really good conductance, it's a conductor, and if it's really bad conductance, it's an insulator. That's how we would describe them. That doesn't mean that everything falls exactly at one end or the other. There's a lot in between. And the units that we would use on conductance are called mohs, which I think is, I just put this in there because I think this is funny. That's ohms backwards. So no one ever, well, people talk about mohs, but they probably will never talk about it in terms of fencing. It's just the reciprocal of an ohm. I just love that it's the backwards spelling of it. It makes my heart happy. Don't worry if it doesn't make yours happy. I'm here today to enjoy it for you. A leak. A low conductance, high resistance path from the fence back to the earth return or the ground. A leak is really an interesting thing because a lot of times we'll talk about having a fence that's shorting out. And there's two things that happen on electric fence. There's leaks and shorts. A leak means that there's a pathway that is occurring that is being used for some amount of electrons. But it is not the majority of the electrons that are going through this pathway. It is a small number that are choosing it. So you have a piece of grass. A grass might occasionally be a decent enough conductor that it's going to take some electrons down to the ground. But it's probably not going to be a really great pathway, and all of the electricity on your fence is not going to go through that piece of grass. It's just not good enough as a conductor to be the primary pathway that's going to be used. But small amounts of those electrons are going to sneak down that pathway and make it back to the ground to complete a circuit.
So when you have, like, sometimes when it's wet like this out, you can actually put a voltmeter on a wooden fence post in a reading on it. So
Sure.
is that what?
Yeah, wood is a great example. So wood by nature is fairly insulative. It tends to fall more towards insulation than to conductance, but when there's a lot of moisture, moisture is an extremely good conductor. Water conducts extremely well. And if there's enough water along or within, just inside that surface of the wood, it becomes a more conductive pathway and we start to leak, especially if we have, if we don't have any sort of insulation on the outside of that wood post, or even if we have some insulation and there's like a jump across some sort of small insulator there, we can get a little bit of electrons sort of jumping an insulator and following down a wood path. Also, you might see it on some wood posts because it's coming back out of the ground, depending on if something's really shorting a fence. Because it could conduct either direction, depending on what's happening. But most times it's because there's a bad insulator or no insulator at all, and without moisture there, it just becomes a leak pathway.
So Morgan, like on a full fencing system, if you have like a whole bunch of leaks, small leaks, they start to add up over time?
Yes. Yeah, because basically what you were doing on that first slide where I showed the fence is you're trying to throw out as many electrons as you can in that pulse. And some of them are just going to be out there. You know, they're just out on that wire. Some of them are always going to sort of sneak away. They're going to find some way to get back to the ground to complete the circuit because that's what they're trying to do. They're not trying to stay on a high charge all the time. The system naturally desires to neutralize itself. You can have a bunch of little pathways and still be okay, but if you get too many of them, then all of a sudden there's not enough charge left, enough electrons left on that wire to create the voltage necessary, that push against an animal when they touch it. So I put in here foliage, cracked insulators, they're a big one, a length of live wire on the ground. Interestingly, it depends on how much wire is touching the ground as to whether it becomes a leak or a short. Like if you just drop your whole fence on the ground, it's shorting probably. But if you just have like one piece of wire that's just touching the ground occasionally, you might still only be leaking. You know, you might not actually have a full-on short on that scenario. And most times when animals touch the fence, they're a leak. The shock that you feel when you touch that fence is not necessarily a short. It depends on, like, if you full-on grab and you really, like, drain that fence, you can short it. But most likely, an animal touching it and getting shocked is really only a leak. They don't normally empty the capacity of the fence when they do that. Depends on the size of the animal and what's happening, but it's kind of scary to think that even when we're doing that, we're not actually necessarily draining the system when we shock an animal or ourselves, because it's not necessarily true. A short, on the other hand, is a high conductance, low resistance pathway from the fence back to the earth return ground. This would be if two wires are touching a ground and a hot wire are touching each other. That is a guaranteed short, because that electricity is going to go right from one wire to the other one. Sometimes we see this on a, instead of having an earth return, we have alternating wires, and they're actually properly grounded, and we have a tree limb or something sit down, and then all of a sudden our hot wire is touching a grounded wire, a true grounded wire. That's a guaranteed short. There's no way we're going to create another pathway that's going to be less resistance than that, because those wires are naturally really conductive. Wire-to-wire shorts are pretty common. Even neutral wires can short, especially if there's metal posts that they're attached to and things like that, because then a neutral wire will hit you know, a steel post and it'll drop right into the ground. That's actually a pretty easy situation. So if you ever see someone that only has half of their wires hot and half of them are neutral, they're not even grounded, but they got metal posts in there, I mean, that's almost guaranteed to be a short if that scenario occurs. Most cases, though, humans, although they're decent conductors and animals are decent conductors, they don't tend to be shorts in most scenarios. High impedance is a term we see a lot in electric fencing, and the reason we see high impedance listed a lot in electric fencing is because earlier energizers or chargers on fences delivered really long pulses of high voltage, low amperage power. And what ended up happening is we used to have some fire hazards with older electric fencing styles that weren't high impedance, because we were pushing out that power and we actually had enough charge, you know, going through some of those grasses and things that we could actually create fire. So a high impedance charger scenario, building like this, what we're essentially doing is we're throwing out really, really fast pulses, and we're not allowing a scenario in which the power can actually create fire. So that's why you will see that term high impedance on chargers now. Oh, sorry, that's why you will see the term low impedance on chargers now. I said that backwards, didn't I? Low impedance charger uses high voltage, higher amperage, but really short bursts. I said that backwards. So the charge becomes shorter, the amperage becomes slightly higher to get the same amount of power out, but because that burst is shorter, we can discharge it and we don't continuously have a charge on those, I would call them not really conductors, but those leaks, those pieces of foliage that are occurring within the system. I misspoke. And then I wanted to go through, last thing before I'm done, is the way I think of electrical relationships, and I'm going to use a water analogy because it's the one that makes sense to me. But before I do that, I just want to just note here, the voltage or potential difference between two terminals is defined as having a value of 1 volt when 1 joule of energy is used in moving 1 coulomb of electrical charge between the two terminals. So for every volt that comes out of a scenario, we know we have 1 joule of energy moving 1 coulomb out on those wires, and if it connects in a full circuit back to that ground, we get a joule of power or energy. And when 1 volt is applied to 1 ohm, the amount of resistance that keeps the flow rate at 1 amp. What we should know about this ultimately is that these relationships exist so that we can actually measure power. It's the reason that we can actually validate how a charger works. We don't know how it works on the fence itself, but we can actually make sure that our chargers meet certain specifications because we can actually measure power. And we can actually then figure out what sort of transformers and things are in those boxes to push out the desired coulombs or electrons onto that wire correctly. If it was me and I was thinking about power, I think a lot of people will use like a piece of pipe or something like that as their analogy. I always like to start this thought process with the thought that there's a water tower attached to my water lines. I don't know if that's good or bad or if other people follow my analogy or not. This is how I think of power. if I want to know how much work I can do in an electric fence, the way I think of this is it's like the height of the water tower. How much water pressure can I get out at my shower head is directly related to whether or not I have enough height on the water tower that's feeding my lines. Has anyone ever lived somewhere where they had terrible water pressure? Yeah, me too. It's awful. It's pretty miserable. And there's a couple reasons that you can have this issue. But the first one is if you don't have enough water pressure on the whole system. And for me, the water tower is like the charger in an electric fence. This is where the actual energy comes from to move the system along. And height is what we use, gravity is what we're using on most city water. City is a relative term here. When we have water pressure, I think of water pressure as actual voltage, and I think of water flow or gallons of water coming into my house as the amperage. Has anyone ever had a shower where you had a terrible shower head? You might dump gallons of water out, but you can't actually get the pressure on that head to actually do that. We actually need both pressure and flow on our water lines to get what we want out of them. So for me, the concept, some people will just talk about water, but pressure really is the accurate way to think about voltage. What you feel out of that shower head is similar to what you feel in terms of voltage on a fence line. And it's not necessarily the same as the amperage on the system. You got a running toilet that runs in your house. Does that mean you can't take a shower? No. It's probably a leak in the system. You got that running, you got a sink running. If you have enough pressure, you can keep running your shower and there's no issue. Now, if you turn on all of your watering system to your animals on your farm, and you have your leaks in your bathrooms, and you're running your sink, and you're running your washer and dryer, whatever, the washer is really the only thing that runs water, but all of that at once, all of a sudden you might have enough leaks in the system that you can't take a shower and get the pressure you want out of it. But any one individually is not an issue. It's just the culmination of a lot of things running at one time that might create enough pressure drop that you really don't get what you want pressure-wise, the feel that you want out of that system. But when you're setting your fence posts and you hit the water line before it even comes into your house right at the main, that's a short. I mean, you can try and take a shower, but there's not any water coming out. You've broken the circuit, right? Before it actually makes it into the house. That would be a short. I don't know if I have any more slides. Do you have any questions? The water analogy to me is the easiest one for me to visualize. So when I try and describe what's happening on an electric fence, this is usually how I'll describe it to someone who's not sure.
So what we wanted to do with this presentation is kind of introduce you to some of the terminology and concepts of electric fencing, something that you wouldn't normally get at a regular extension meeting. I know that was a lot of...
It's a lot of terminology.
But that's what I asked Morgan to do, and I think she did a good job of kind of bringing it together again. I guess, can I ask you and maybe Buddy or Jeremy, what are you going to go over the components of electric fence charger? Anybody going to do that in the presentation? As far as the internal circuitry? Yeah, how it works inside.
I can talk about it a little bit.
I want to hear from the engineer's perspective. Probably more. Okay. You want to talk just a little bit about how it works?
So there's two styles of energizers or fence chargers. And one is an AC powered one and one is a battery powered one. So any solar chargers or anything where you're changing out batteries all the time is basically a DC driven circuit. And what that means is that all of your power in that fence comes out of that battery. Same joules that you're getting in a battery that you'd be getting out of your AC, not necessarily equivalent, but both of them are going to provide joules in different ways. So if you're pulling from one that uses a battery system, you're pulling from something that's 6 or 12 volts and a lot of amps, and you're converting it with a huge set of transformers, similar to what you see on your electric lines. You're bringing in, you ever see big electric lines come in, transformer, and then smaller lines go out to houses? It's the same concept. Inside the box, there's transformers that are basically moving this power from being a lot of amperage and less voltage to more voltage, less amperage. So we're basically modifying the way that this works. For my water analogy here, right, we're talking about pressure versus flow. We're basically changing the size of the pipe, right? We're putting a lot more pressure on the situation and reducing the flow. And that's basically what a transformer does within the box.
So you're changing in a DC system or a battery system?
In an AC or a DC system, both of them are going to convert lower levels of voltage to higher levels of voltage by reducing amperage. Both, the difference is in a DC, we're working from somewhere around 6 or 12 volts, usually 6, and in an AC circuit, we're working off of 120 volts as our starting point. Also in an AC, we're working off of a pulsed power coming in, and on a DC, we're going to have to, both of them, we're going to have to create our own pulses anyway, because we're not using the same pulse rate that is in the, not the 60 hertz that's in the wall. We're using a much higher hertz, higher pulse rate. 60 hertz would be much more in line with actually the high impedance older chargers. Now we've put in a much faster pulse in the scenario, low impedance. Is that how you would describe it?
Then you also have the capacitor.
Yes. And the capacitors basically act as a bank for the power to be able to flow out. What you're essentially doing when you throw out this power is you have some amount of electrons that you're pushing out instantaneously every time there is a pulse. Does that make sense? And so what you really want to do is you want to have both a capacity at the charger that you can push out, and usually there's more capacity in the electric charger in the Energizer than is what's getting pushed out each time. And that's important because that allows you to sort of handle if there's, especially on like a solar box, and there's not sunlight, that even if there's a couple leaks, that you're not going to kill your fence immediately because there's no solar feeding it right at that moment in time. And that's why you have the battery in there as well.
Are there any other questions for Morgan?
No.
Can you elaborate on, with the newer technology, why we see the grass and leaves get dehydrated and turn brown versus the old technology with leaf burners where it would just dry out and possibly start fires? What's actually causing that plant to turn brown in the new technology?
So basically what's happening is those electrons, as they transfer through there, they're using that water to go into the ground. And there's a couple things that are happening. One, there is naturally resistance that's occurring. So there is, I don't know if it's exactly heating of the water, but it's a resistance within the plant itself because the plants, the xylem and the phloem in the plants basically is carrying that water in a pathway down. And it's the reason that really up at that top where all that electricity feeds in, until it actually works its way down those cells of basically all water, it's basically killing the top of that plant. But because the plant's still alive, it just carries it right down in there. Does that help?
Yeah, and we're going to see some good examples today. We've got a fairly large capacity Energizer, it's 28 joules, and you're going to see some good examples of some thistles that have started to dehydrate and shrivel up for the, especially the wire. And you'll also see pads
Yeah, with the older style high impedance ones, especially with the higher resistance that's on like poly wires and things like that, it just creates so much friction and heat that, because those pulses sort of were prolonged, you had the capacity to actually heat the plant to the point of actually creating a fire. But you had resistance, usually, sometimes you could do it off a wire. A lot of times you did it off of like poly wire or smaller wires that had more resistance on them naturally anyway. So it makes it even higher risk, I guess. Is that how you would describe it? Yeah, that's how I would describe it.
Any thoughts on or comments on induction? A lot of times producers will contact us, I'm sure a lot of agents, hot gates and hot brace wires.
Okay, so like I said before, the way that that power runs, it runs on the outside of the wire. And those electrons are not tied to the wire. It's not like they can't move off of a wire. So what's essentially happening is we're putting pressure on that wire, so that voltage sits on the outside. It doesn't go hugely far away from the wire. It's not like, it's moving miles in thin air. It's not going to do that. But especially if you have not enough insulation between that and a wire that's attached to a gate, it can jump. Those electrons can move small distances through the air to make it, and so the term induction really essentially it's more like a magnetic term for it, but essentially that power is moving across what is not really a good conductor or technically a great insulator. It's something that sort of sits in the middle, but it has the capacity to move across short areas of air because there's enough charge at some point and there's not enough insulation to stop it from going. And it's finding itself a leak. And it is really annoying when you find a gate that's hot. I thought this is a story time by Morgan. I was trying, after I'd broken my foot, but before I had the surgery, I was trying to diagnose some electrical problems I have in my water lines. And I had a pulsing in a gate, and the fence that's attached to that gate is not hot. So I was thinking to myself, I have stray voltage from a heater in my water tank that's right beside this gate. And then I found out that that was not the case. I actually had one wire that was jumping from the next fence onto a wire onto that fence because they were really close to each other, where the two fences tied together. And I had that sort of induction. It was running down that wire, and that wire was directly in contact with my gate. So I really was shocking myself off of my fence. But it was not easy to track because I wasn't instinctively looking for it to be there because it had to make sort of two jumps to hit onto my fence, which is why it wasn't so painful that I continued to track it down and left the fence on while I was doing so. That and the fact that I thought it was in my water tank heater. But it's not unusual to have that, especially if you're not paying attention. Or we're going to use the fault finders today. Those are so useful. That's the only reason I found it finally, is because I actually used fault finders and it sent me back to my fence and not, it kept sending me back towards the main line, and so.
So one of the exercises this afternoon will be actually finding faults in fence using the fault finder. And I've got about 20 fault finders so everybody can have one look for faults. You can't take it home though, they're like $100 a piece, and I can't. You have to turn it back in. Anything else for Morgan? I'm really
I guess there's a chance that you could be dangerous, but it doesn't seem like you could gain enough power.
It's a pretty big air gap, right?
There's a huge air gap, and at the end of the day, if there was pushing enough power out, I would assume some of that power would find some other routes to ground. And I also would assume if you were losing enough power to do that, eventually the electric company would get concerned about it. Because you basically would, now I will also say I have also seen the electric company miss huge amounts of power in other places within, after meters or right at meters and things. So they might not notice for a long time, but I'm trying to think if you could gain enough power off of that kind of inductance to really hurt yourself. I struggle to see how you could without it trying to ground itself. The difference is that you're not probably getting, the voltage amperage relationship isn't going to be what you want on those lines. So I'm trying to decide if you could throw enough amperage on it to really create, at low voltage, a problem. It's also not really designed to conduct like that. That wire is designed for high voltage application. It's not really designed for low voltage, high amperage. The style of wire that we're using shouldn't necessarily, wouldn't be our goal if we were doing that, I don't think. Does that make sense? Like, I would think if I really wanted that, I would be looking for bigger wire, copper, or something with a really highly conductive material to really try and push it if I wanted to try and really pull power out of that inductance scenario. You probably could, under a really terrible scenario, though, I guess. Depends on how big they are. A hum. Oh, yeah.
So is there ever such a thing as a comfortable shock? That would be more comfortable than getting shocked by 28 joules. I had a question on kind of the theory of the Energizer. So you're sending these pulses out, like I think you said 330 in sections, something, right? So you send these electrons out the line. They're running on the outside of the line, right? And then you stop and you have a period of no electrons going out. What happens to the electrons that you send out on the line? Because they're not making a circuit, right? Unless there's a short or a leak or something's touching it, right?
Yeah, so, you know, the scenario people a lot of times will say it's like sort of like filling a line, like you're sending them out and they just stay out there, but that's not really true. They're out and back. Like it's out and back. Yes. You're not fast enough anymore, but with a high impedance you could have been. It's unlikely you can now. You really have to be very, very good. Much faster twitch muscles than I have. Yeah. So an amplifier, basically, what you're doing is you're almost resetting the scenario. So what's happening is you're trying to send out all of this signal and bring it back. It's almost an out and back is what's happening, right? You're sending them out and back. It's almost like they're going out and then they're, yeah, I mean, almost like a wave. Like it's not really out and back, but it's almost like there is true pulses in this. So an amplifier is designed, as you start to get further out and there's some resistance against it, you're trying to re-normalize the way that power is coming. Does that make sense? You're almost trying to make it go back to is that how you would describe it? An amplifier? That's how I would describe one. Oh. We don't normally see them here because, to be completely honest, we just don't run long enough fences here to really need them. I guess if you had higher resistance, maybe you'd get to a scenario and you wanted to run a smaller box. Maybe you could use an amplifier, but we shouldn't need one here. There'd be no reason to use one around here. But an amplifier shouldn't have like batteries in it. Like it shouldn't have, it shouldn't be feeding your system in quite the same way, if that makes sense.